cosm. Whoosh.
You know what keeps me up at night? It's not the vastness of space. It's not even the mysteries we haven't solved yet. It's what happens when we finally get the answers we've been seeking for centuries, only to discover that the universe has been playing by completely different rules than we thought. And that's exactly what's happening right now with the James Webb Space Telescope. Let me set the stage for you. On Christmas Day 2021, humanity launched what is essentially a time machine into space. Not the kind you see in science fiction movies, but something far more profound. The James Webb Space Telescope, with its massive golden mirrors stretching over 21 feet across, gives us the power to look back through time itself. Every photon of light it captures has been traveling through the void for billions of years, carrying with it the story of our cosmic origins. But here's where things get interesting. We built this telescope expecting to confirm what we thought we knew about the universe. We had our theories, our models, our predictions all lined up like dominoes. We were ready to watch them fall into place, one after another, painting a picture of cosmic evolution that would finally make sense. Instead, James Webb has been knocking those dominoes over in ways we never anticipated, and what's emerging from the chaos is a universe that's far stranger, far more complex, and infinitely more fascinating than anything we imagined. Picture this: you're an astronomer, and you've just received data from the deepest image ever captured by human technology. You're expecting to see the universe in its infancy, a chaotic mess of primitive galaxies slowly taking shape. You know what you should find because the theory is solid, tested, refined over decades. But when you look at the data, your coffee cup stops halfway to your mouth. Because what you're seeing shouldn't exist. Not according to everything we thought we knew. The galaxies staring back at you from the edge of time aren't struggling to form. They're not primitive or simple. They're massive, structured, sophisticated. They have spiral arms, they have bright cores, they look almost like the galaxies we see in our cosmic neighborhood today. Except these galaxies are appearing just a few 100 million years after the Big Bang, when the universe was barely 3% of its current age. It's like finding a fully formed skyscraper on a construction site where the foundation was poured yesterday. Now, I want you to understand what this means. We have a timeline for how galaxies should form. It's called hierarchical structure formation, and it's been the backbone of our understanding for decades. Small structures form first, then they merge and grow larger over billions of years. It's a slow, gradual process, like building a cathedral stone by stone. But James Webb is showing us cathedrals appearing almost overnight in cosmic terms. And that's not just surprising, it's revolutionary. Let me give you some specifics, because the details here are absolutely mind-blowing. Webb has identified galaxies like Glass C13, which existed when the universe was just 300 million years old. To put that in perspective, if the universe's current age were compressed into a single year, we're looking at galaxies that formed on January 3rd. And this galaxy isn't alone. There's Glass C11, there's HD1, there are dozens of these impossibly early, impossibly massive galaxies scattered across Webb's deep field images. But mass isn't the only shocking feature. These early galaxies are producing stars at rates that should be physically impossible. We're talking about star formation happening 10, 20, sometimes 50 times faster than what our models predict. It's like watching a movie on fast forward, except this isn't a movie, this is reality. And reality, as it turns out, has no obligation to conform to our expectations. Here's where it gets even more fascinating. When you look at these ancient galaxies with Webb's infrared eyes, you see something that challenges another fundamental assumption. These galaxies aren't just big and bright. They're chemically mature. They contain elements heavier than hydrogen and helium. Elements that should take generations of stars to produce. You need stars to be born, live their lives, and die in spectacular supernovae to create these heady elements. That process should take time, lots of time. But these galaxies are showing us chemical compositions that suggest multiple generations of stars have already come and gone when the universe was barely out of diapers. Think about what that means for a moment. The cosmic clock is running faster than we thought. The universe's childhood was far more eventful, far more productive than our theories suggested. It's as if we've been trying to reconstruct the story of a person's life, and we thought their first 5 years were spent learning to walk and talk. But then we discovered photographs showing them graduating from college during that same period. Now, let me take you deeper, because the rabbit hole goes much further than just early galaxies. Webb has been staring into regions of space called the Hubble Ultra Deep Field and its own deep field observations, looking at patches of sky no bigger than a grain of sand held at arm's length. And in these tiny windows to the universe, Webb has counted galaxies. Lots of galaxies. More galaxies than we expected to find. Here's the problem. When you add up all the mass in all these galaxies, and you account for how quickly they formed, you run into what scientists are calling the impossible early galaxy problem. There simply wasn't enough time after the Big Bang for normal matter to cool down, clump together, and form structures this massive this quickly. The universe should have been too hot, too smooth, too uniform. The tiny quantum fluctuations from the Big Bang that seeded galaxy formation shouldn't have been able to grow this fast. Unless something else was going on. Unless our understanding of the early universe is missing something crucial. This is where dark matter enters the story, but not in the way you might expect. We've known about dark matter for decades. It's the invisible stuff that makes up about 85% of all matter in the universe. We can't see it, we can't touch it, but we know it's there because of how it affects normal matter through gravity. Dark matter should have been the scaffolding that helped galaxies form, providing the gravitational wells that normal matter could fall into and start building stars and galaxies. But here's the twist: even with dark matter doing the heavy lifting, the galaxies Webb is seeing are forming too fast. It's like dark matter is somehow more efficient in the early universe than it is today. Or maybe there was more of it than we thought. Or maybe, and this is the really exciting possibility, maybe dark matter behaves differently under the extreme conditions of the early universe. Some physicists are now proposing that dark matter might not be cold and slow-moving like we've always assumed. Maybe in the early universe, dark matter was hot, or warm, or interacting with normal matter in ways we haven't considered. Maybe there are different types of dark matter, and the kind that dominated the early universe had properties that allowed it to clump together faster, pull normal matter together more efficiently, and kickstart galaxy formation on an accelerated timeline. But wait, there's more. Because while Webb has been rewriting our understanding of galaxy formation, it's also been discovering things that challenge our models on completely different fronts. Let me tell you about the stars that shouldn't exist. Webb has been analyzing the chemical compositions of some of the oldest stars in these ancient galaxies, and it's finding stars with metal abundances that don't match our predictions. In astronomy, everything heavier than hydrogen and helium is called a metal, and the amount of metals in a star tells you about its history and the history of the universe around it. The first generation of stars, the ones we call population 3 stars, should have 0 metals because they formed directly from the primordial hydrogen and helium left over from the Big Bang. We've never actually seen a population 3 star. They should have died billions of years ago, and they should be incredibly rare. But we can look for their signatures in the next generation of stars, which should have very low metal content. Webb is seeing stars in the early universe with metal abundances that are much higher than expected, suggesting that the process of metal enrichment happened incredibly quickly. Stars were being born, living, dying, and seeding the cosmos with heavy elements on timescales that seem impossibly short. And here's what really bakes your noodle. If stars were forming and dying this quickly in the early universe, if galaxy formation was happening at these accelerated rates, then maybe the formation of the first black holes, the seeds of the supermassive black holes we see at the centers of galaxies today, maybe that process was also happening faster than we thought. Which brings me to one of the most shocking discoveries Webb has made. At the center of many of these impossibly early galaxies, Webb is detecting the signatures of supermassive black holes. Not just any black holes, but monsters with masses millions or even billions of times that of our Sun. And they're there when the universe is less than 1 billion years old. Now, if you know anything about black holes, you know they grow by consuming matter. They start small, maybe from the collapse of a massive star, and then they gradually accumulate mass over time by pulling in gas, dust, and occasionally other stars. It's a process that should take billions of years to create the supermassive black holes we see today. But Webb is showing us that these giants already existed when the universe was in its infancy. How do you grow a billion solar mass black hole in less than a billion years? The math doesn't work, not with our conventional understanding. A black hole growing at the maximum theoretical rate, gorging itself on matter as fast as physics allows, would still need more time than the early universe provided. Unless these black holes didn't start small. Unless they were born massive. Some theorists are proposing that in the early universe, conditions might have been right for direct collapse black holes to form. Instead of starting from a single star, entire regions of gas might have collapsed directly into black holes with masses of 10,000, 100,000, even 1,000,000 times that of the Sun. These seeds could then grow into the supermassive black holes we observe, and the timeline would make sense. But here's the catch: we don't have a confirmed mechanism for how direct collapse black holes would form. We have ideas, we have simulations, but we've never observed this process. Webb might be giving us the evidence we need, but it's also raising new questions. If direct collapse black holes were common in the early universe, why don't we see them forming today? What was special about the conditions in the young cosmos that allowed this to happen? Let me shift gears for a moment and talk about something that might seem unrelated but ties into all of this in a profound way. Webb has been looking at the cosmic microwave background radiation, not directly, but through its effects on the universe. The cosmic microwave background is the afterglow of the Big Bang, the oldest light in the universe, and it carries with it a snapshot of what the universe looked like just 380,000 years after its birth. For decades, we've been measuring the cosmic microwave background with incredible precision, and it tells us that the early universe was remarkably smooth and uniform. There were tiny variations in density, quantum fluctuations that got stretched to cosmic scales during inflation, and these variations eventually became the seeds of all cosmic structure. But the variations were small, less than 1 part in 100,000. So here's the puzzle. If the early universe was that smooth, how did it produce such massive, well-formed galaxies so quickly? The fluctuations we see in the cosmic microwave background should have taken much longer to grow into galaxies. It's like looking at a perfectly calm pond and then, a second later, finding massive waves crashing on the shore. Where did the energy come from? What accelerated the growth of these structures? One possibility that's gaining traction is that we're missing something in our model of the early universe. Maybe inflation, the period of exponential expansion that happened in the first fraction of a second after the Big Bang. Maybe inflation left behind more structure than we realized. Maybe there were pockets of space that were denser than others, regions where matter could start clumping together earlier and faster. Or maybe, and this is where things get really speculative, maybe the universe went through a second phase of rapid change after inflation. Some cosmologists are proposing that there might have been a period of reheating, where the energy from inflation got converted into matter and radiation, and maybe this conversion wasn't perfectly smooth. Maybe it created additional density fluctuations that our current models don't account for. But let's go even deeper. Because Webb isn't just challenging our understanding of galaxy formation and black holes. It's forcing us to reconsider some of the most fundamental assumptions about cosmology itself. You've probably heard of the Hubble tension. It's one of the biggest puzzles in modern cosmology, and Webb is right in the middle of it. The Hubble tension refers to a discrepancy in measurements of how fast the universe is expanding. When we measure the expansion rate using the cosmic microwave background, we get one number. When we measure it using observations of distant supernovae and other objects, we get a different number. And these numbers don't agree. Now, you might think a small discrepancy isn't a big deal, but in science, especially in cosmology, precision matters. The difference between these measurements is statistically significant, meaning it's unlikely to be just random error. And if it's real, if the universe really is expanding at different rates depending on how we measure it, then something is seriously wrong with our standard model of cosmology. Webb has been adding fuel to this fire by making its own measurements of the expansion rate, and guess what? Its measurements tend to agree with the higher value, the one that doesn't match the cosmic microwave background. This is significant because Webb is using different techniques and observing different objects than previous telescopes, and yet it's confirming that there's a real problem here. So what could explain the Hubble tension? One possibility is that our understanding of the early universe is incomplete. Maybe dark energy, the mysterious force that's causing the universe's expansion to accelerate, maybe dark energy has changed its properties over cosmic time. Maybe it was weaker in the early universe and stronger today, or vice versa. If dark energy is evolving, that could explain why different measurement methods give different results. Another possibility is that there's something wrong with our measurements. Maybe we're not accounting for some subtle effect that's throwing off our calculations. But the problem with this explanation is that multiple independent teams using different methods are all finding similar discrepancies. It's hard to imagine that everyone is making the same mistake. Or maybe, and this is the most exciting possibility, maybe we're discovering the first crack in the standard model of cosmology. Maybe the universe is trying to tell us that our understanding of gravity, or dark matter, or dark energy, or even the Big Bang itself, needs to be revised. Let me tell you about something else Webb has found that relates to all of this. Webb has been studying what's called the reionization epoch, the period when the first stars and galaxies started forming and their ultraviolet light began ionizing the hydrogen gas that filled the universe. Before reionization, the universe was dark and opaque, filled with neutral hydrogen that absorbed most light. After reionization, the universe became transparent, and light could travel freely across cosmic distances. We thought we understood reionization pretty well. We thought it was a gradual process driven by the ultraviolet light from the first galaxies, and we thought it took several 100 million years to complete. But Webb is showing us that reionization might have happened faster and earlier than we expected. And it might have been driven by sources we didn't anticipate. Webb has detected galaxies that existed when the universe was less than 400 million years old, during what should have been the heart of the reionization era. And these galaxies are producing ultraviolet light at prodigious rates, enough to ionize vast regions of space around them. But here's the interesting part. When you add up all the ultraviolet light from all the galaxies Webb can see, it's still not quite enough to explain how quickly reionization happened. So where's the missing light coming from? One possibility is that there are even more galaxies out there that Webb can't see yet, galaxies that are too faint or too distant to detect with current observations. But another possibility is that there were other sources of ionizing radiation in the early universe. Maybe the first black holes, as they consumed matter and radiated energy, maybe they contributed significantly to reionization. Or maybe there were exotic sources we haven't even considered yet, like decaying dark matter particles or primordial black holes evaporating through Hawking radiation. Now, I want to take you on a journey to one of the most distant objects Webb has observed, because this particular discovery encapsulates everything I've been talking about. It's a galaxy called JADES GSC 13-0, and it exists approximately 13.5 billion light-years away, which means we're seeing it as it was just 300 million years after the Big Bang. When I say we're seeing this galaxy as it was, I mean that literally. The light from JADES GSC 13-0 has been traveling through space for more than 13 billion years. When that light started its journey, Earth didn't exist. The Sun didn't exist. The Milky Way was still forming. Dinosaurs wouldn't appear for another 13 billion years. And yet, here we are, capturing those ancient photons with our telescope and reconstructing what this galaxy looked like at the dawn of time. JADES GSC 13-0 is tiny by cosmic standards, maybe only a few 100 million times the mass of the Sun and stars. But it's bright, incredibly bright for its size, which means it's forming stars at a furious rate. It's compact, densely packed with young, hot stars that are pumping out ultraviolet light. And spectroscopic analysis shows that it already contains elements heavier than hydrogen and helium, which means it's not a first-generation galaxy. It's been building stars, those stars have been dying, and their deaths have enriched the galaxy with heavy elements. All of this happened in less than 300 million years. To put that in perspective, 300 million years is about the time between when dinosaurs first appeared on Earth and today. Imagine if dinosaurs had evolved from simple organisms, built a civilization, developed technology, and reached the stars in that time frame. That's essentially what this galaxy did on a cosmic scale. But here's what really gets me about JADE's GSZ 13-0 and galaxies like it: they're not anomalies. Webb has found dozens, perhaps hundreds of similar galaxies scattered across the early universe. They're all forming stars at breakneck speeds, they're all more massive and more evolved than they should be, and they're all challenging our understanding of how cosmic structure emerges from the chaos of the Big Bang. And speaking of chaos, let me tell you about Webb's observations of galaxy collisions in the early universe. We know that galaxies grow partly through mergers, with smaller galaxies colliding and combining to form larger ones. This process should have been common in the early universe when galaxies were closer together and the cosmos was more crowded. And indeed, Webb is seeing evidence of galaxy interactions and mergers in its deep field images. But here's what's surprising: some of these merging galaxies are already quite massive and structured before they collide. It's not just simple blobs of stars crashing together. These are galaxies with defined morphologies, with disks and bulges, interacting with each other. And the merger process itself seems to be triggering intense bursts of star formation, creating what astronomers call starburst galaxies. These starburst galaxies are producing stars at rates of hundreds or even thousands of solar masses per year. For comparison, the Milky Way produces about 1 or 2 solar masses worth of new stars each year. So these early galaxies are outpacing our home galaxy by factors of hundreds or thousands. And all that star formation is happening in a relatively small volume of space, creating incredibly dense stellar environments where stars are packed much closer together than they are in the Milky Way. Now, imagine being a planet orbiting a star in one of these starburst galaxies. Your night sky wouldn't look anything like ours. You'd have thousands of bright stars visible to the naked eye, so many that you might not even have a concept of darkness. And every few hundred years, you'd witness a supernova explosion, a dying star briefly outshining the entire galaxy. The radiation from all these stars and supernovae would make the environment incredibly hostile to life as we know it. But it would also be spectacularly beautiful and energetic. Let me shift gears and talk about something that Webb has revealed about the structure of the universe on the largest scales. When you map out the distribution of galaxies across billions of light years, you don't find a random scattering. You find structure. Galaxies are organized into clusters, and those clusters are organized into superclusters, and those superclusters are connected by filaments of galaxies that stretch across hundreds of millions of light years. Between these filaments are vast voids, regions with very few galaxies. This cosmic web structure is predicted by our theories of structure formation. The initial quantum fluctuations from the Big Bang got amplified during inflation, and then dark matter started clumping together under its own gravity, creating a web-like network of dense regions connected by filaments. Normal matter followed the dark matter, flowing along these filaments and collecting at the intersections where galaxy clusters form. Webb has been tracing the cosmic web back to earlier times, looking at how this structure emerged and evolved. And what it's finding is fascinating. The cosmic web was already taking shape remarkably early, with filaments and clusters beginning to form when the universe was less than 1 billion years old. This is earlier than many models predicted, and it suggests that the seeds of large-scale structure were stronger or grew faster than we thought. But here's where things get really interesting. Webb has also been studying what's called the Lyman alpha forest, which is a series of absorption lines seen in the spectra of distant quasars. These absorption lines are caused by clouds of neutral hydrogen gas scattered along the line of sight between us and the quasar. By analyzing these absorption lines, astronomers can map out the distribution of gas in the early universe and see how it's clustered along the cosmic web. What Webb is finding is that the distribution of gas doesn't always match what we expect from our models. There are regions where gas seems to be clumping together more strongly than predicted, and regions where it seems more dispersed. This could be telling us something important about how gas cooled and collected in the early universe, or it could be revealing the effects of energy injection from the first stars and black holes. You see, when the first stars formed, they didn't just shine peacefully. They were massive, hot, and short-lived, and when they died, they exploded as supernovae, releasing tremendous amounts of energy into their surroundings. This energy heated the gas around them, blowing it outward and creating bubbles of hot, ionized gas. These bubbles could grow and merge, affecting how gas flowed through the cosmic web and potentially regulating where new galaxies could form. Similarly, the first black holes, as they consumed matter, would have released energy in the form of radiation and powerful jets. These jets could extend for hundreds of thousands of light years, plowing through the surrounding gas and creating shockwaves. This process, called feedback, is crucial for understanding galaxy formation because it can both trigger new star formation by compressing gas and suppress it by heating gas and blowing it away. Webb is giving us the first detailed look at how feedback operated in the early universe, and it's revealing a complex interplay between star formation, black hole growth, and gas dynamics. Some galaxies show evidence of strong outflows, with gas being expelled at speeds of hundreds or thousands of kilometers per second. Other galaxies seem to be efficiently retaining their gas and converting it into stars. Understanding what determines these different outcomes is one of the key questions Webb is helping us answer. Now, let me tell you about one of the most profound implications of all these discoveries. If galaxies, stars, and black holes were forming this quickly in the early universe, if the cosmos was this active and productive when it was young, then the conditions for life, at least the basic building blocks of life, might have appeared much earlier than we thought. Life as we know it requires certain elements: carbon, nitrogen, oxygen, phosphorus, sulfur. These elements are created inside stars and dispersed into space when those stars die. The first generation of stars contained only hydrogen and helium, so no planets and certainly no life could form around them. But the second generation of stars, enriched by the deaths of their predecessors, could have had rocky planets with the chemistry necessary for life. Webb is showing us that this chemical enrichment happened remarkably quickly. Within a few 100 million years of the Big Bang, there were stars and galaxies with substantial amounts of heavy elements. This means the clock for the emergence of life in the universe might have started ticking much earlier than we realized. While Earth wouldn't form for another 9 billion years, there might have been other planets, orbiting other stars, in other galaxies, where life began when our universe was still in its youth. Now, I'm not saying Webb has found evidence of life in the early universe. It hasn't, and it probably couldn't with its current instruments. But what Webb is doing is expanding the potential timeline for life in the cosmos. It's showing us that the universe became capable of supporting life, at least chemically, much earlier than we thought. And if life could have emerged earlier, then it could have had more time to evolve, to become complex, to perhaps even develop intelligence and technology. This has profound implications for the search for extraterrestrial intelligence. If intelligent life could have arisen billions of years before it did on Earth, then there might be civilizations out there that are billions of years more advanced than us. Imagine a civilization that had a billion-year head start on technology. What could they have accomplished? Could they manipulate matter at the quantum level? Could they engineer stars and galaxies? Could they have found ways to transcend the physical limitations we consider fundamental? These are the kinds of questions that Webb's discoveries are prompting us to ask. And while we don't have answers yet, the very fact that we're asking these questions is a testament to how much this telescope is changing our perspective on the universe. But let me bring us back to something more concrete, because there's another aspect of Webb's discoveries that I haven't fully explored yet. Webb isn't just looking at distant galaxies. It's also studying objects much closer to home, and what it's finding is equally surprising. Webb has been observing exoplanets, planets orbiting other stars, and analyzing their atmospheres using a technique called transmission spectroscopy. When a planet passes in front of its host star from our point of view, a tiny fraction of the star's light passes through the planet's atmosphere. By analyzing that light, Webb can identify the chemical signatures of gases in the atmosphere. And what Webb has been finding in some of these exoplanet atmospheres is unexpected. There are planets with chemical compositions that don't fit neatly into our categories. There are planets with clouds made of exotic materials like silicate minerals or even molten rock. There are planets with atmospheres rich in carbon-bearing molecules, suggesting chemistry very different from what we see on Earth. One planet in particular, called K2-18b, has captured astronomers' attention. It's a sub-Neptune exoplanet, meaning it's larger than Earth but smaller than Neptune, and it orbits in the habitable zone of its star, the region where temperatures might allow liquid water to exist. Webb's observations of K2-18b have detected carbon dioxide and methane in its atmosphere, and there are hints, though not yet confirmed, of a molecule called dimethyl sulfide. Now, why is dimethyl sulfide interesting? Because on Earth, it's primarily produced by biological processes, particularly by marine phytoplankton. If dimethyl sulfide really is present in K2-18b's atmosphere in significant quantities, and if we can rule out non-biological sources, then it might be a biosignature, a sign that life exists on this distant world. But, and this is a big but, we have to be incredibly careful here. K2-18b is probably not like Earth. It's likely a water world, possibly with a thick hydrogen-helium envelope surrounding a deep global ocean. The pressures and temperatures in such an environment would be extreme, and it's not clear whether life as we know it could survive there. Moreover, the detection of dimethyl sulfide is preliminary and needs to be confirmed with more observations. Still, the fact that Webb can detect molecules in exoplanet atmospheres at this level of detail is revolutionary. Before Webb, we could only study the atmospheres of the hottest, largest planets, gas giants orbiting close to their stars. Now, Webb is beginning to probe smaller, more temperate worlds, and with future observations, it might be able to study planets that are truly Earth-like. Imagine what that means. Imagine if Webb or its successors could analyze the atmosphere of a planet similar to Earth and find oxygen, methane, and other gases in ratios that could only be explained by the presence of life. That would be one of the most profound discoveries in human history, answering a question that has haunted us for millennia. Are we alone in the universe? But even without finding life, Webb's studies of exoplanets are teaching us about the incredible diversity of worlds that exist. We've found planets where it rains iron, planets where winds blow at supersonic speeds, planets so hot that rocks vaporize, and planets so cold that methane freezes. We've found planets orbiting binary stars, planets orbiting the dead remnants of stars called white dwarfs, and even free-floating planets that don't orbit any star at all. This diversity challenges us to expand our thinking about what a planet can be and where life might arise. We used to think that life required a planet very similar to Earth, orbiting a star similar to the Sun. But now we're realizing that the universe is far more creative than we gave it credit for. Life might thrive in environments we consider extreme or impossible. And if that's true, then life might be far more common in the universe than we dared to hope. Let me take you back to the deep universe for a moment, because there's another aspect of Webb's discoveries that deserves attention. Webb has been studying some of the most distant supernovae ever observed, stellar explosions happening in galaxies billions of light years away. These supernovae are important because certain types, called Type Ia supernovae, are incredibly useful as cosmic distance markers. Type Ia supernovae occur when a white dwarf star, the dense remnant of a sun-like star, accumulates matter from a companion star until it reaches a critical mass and explodes. Because this explosion happens at a specific mass threshold, all Type Ia supernovae have roughly the same intrinsic brightness. By comparing their apparent brightness as seen from Earth with their known intrinsic brightness, astronomers can calculate how far away they are. This technique was used in the late 1990s to discover that the universe's expansion is accelerating, a finding that led to the concept of dark energy and earned a Nobel Prize. Webb is now pushing this technique to greater distances and earlier times. And what it's finding is that supernovae in the early universe look slightly different from those nearby. The differences are subtle, but they're real. Early Type Ia supernovae seem to be somewhat more luminous, and they evolve slightly faster than their modern counterparts. This could be because of differences in the chemical composition of stars in the early universe, or it could be telling us something about how white dwarf stars explode. Either way, these observations are helping us refine our understanding of supernovae and improve their use as distance markers. But here's why this matters beyond just measuring distances. If we don't fully understand how supernovae work, If their properties change over cosmic time in ways we haven't accounted for, then our measurements of the universe's expansion rate might be systematically off. This could be part of the explanation for the Hubble tension. Maybe the universe isn't really expanding at different rates depending on how we measure it. Maybe our measurements are being thrown off by evolution in the properties of the objects we're using as distance markers. Sorting this out is going to require a lot more data and a lot more work, but it's exactly the kind of question that Webb is uniquely positioned to answer. By observing supernovae across cosmic time, by studying their properties in detail, Webb can help us understand whether they're reliable cosmic yardsticks or whether we need to recalibrate our measurements. Now, let me tell you about something that Webb has observed that's both beautiful and scientifically important: stellar nurseries. These are regions of space filled with gas and dust where new stars are being born, and Webb's infrared eyes can peer through the dust to see what's happening inside. One of the most famous images Webb has captured is of the Carina Nebula, a massive star-forming region about 7,500 light-years from Earth. Webb's image reveals towering pillars of gas and dust, sculpted by the intense radiation from young, hot stars. At the edges of these pillars, you can see bright spots where new stars are just beginning to form, their light starting to shine through the surrounding material. But what's remarkable isn't just the aesthetic beauty of the image. It's what the image reveals about the star formation process. Webb can see protostars, infant stars still surrounded by the disks of gas and dust from which they're accreting matter. It can measure the temperature and composition of these disks, telling us about the conditions in which planets will eventually form. It can track how jets of material are being launched from these protostars, carrying away angular momentum and allowing the star to continue growing. In short, Webb is giving us a detailed, almost real-time look at how stars are born. And what it's showing us is that star formation is messy, chaotic, and incredibly dynamic. It's not a smooth, orderly process. It's violent and turbulent, with shockwaves from nearby supernovae triggering new waves of star formation, with stellar winds and radiation sculpting the gas, with gravity trying to pull everything together while pressure tries to push it apart. Understanding this process in detail is crucial because every star, including our Sun, formed in a region like this. The Sun was born about 4.5 billion years ago in a stellar nursery somewhere in the Milky Way, probably surrounded by hundreds or thousands of sibling stars. Those siblings have long since drifted apart, scattered across the galaxy by gravitational interactions, but they're out there somewhere. And studying stellar nurseries today helps us understand the conditions in which the Sun formed, which in turn helps us understand how Earth and the other planets of our solar system came to be. The chemical composition of the Sun and planets was set by the composition of the gas cloud from which they formed. The dynamics of the protoplanetary disk around the young Sun determined where the planets ended up. And the environment of the stellar nursery, with nearby stars and supernovae, might have influenced the early evolution of our solar system in ways we're only beginning to appreciate. Webb has also been studying brown dwarfs, objects that are too massive to be planets, but not massive enough to sustain hydrogen fusion in their cores like true stars. Brown dwarfs occupy this twilight zone between planets and stars, and they're fascinating in their own right. They have atmospheres, they have weather patterns with clouds and storms, and some of them have temperatures cool enough that water vapor can exist in their atmospheres. By studying brown dwarfs in star-forming regions, Webb is helping us understand the boundary between planet and star formation. Are brown dwarfs just failed stars that didn't gather enough mass? Or are they superplanets that formed like Jupiter but in isolation? The answer might be different for different brown dwarfs, and understanding the full spectrum of object formation, from planets to brown dwarfs to stars, is one of the goals of modern astronomy. Let me now take you to something truly exotic that Webb has been studying: gravitational lenses. When light from a distant object passes near a massive foreground object like a galaxy cluster, the foreground object's gravity bends the light, acting like a lens. This can create multiple distorted images of the background object, or it can amplify the background object's light, making it appear brighter than it really is. Gravitational lensing is useful for two reasons. First, it allows us to see objects that would otherwise be too faint to detect. The magnification from a massive galaxy cluster can boost the light from a distant galaxy by factors of 10 or more, bringing it within Webb's detection range. Second, the details of how light is bent tell us about the distribution of matter in the lens, including dark matter, which we can't see directly but which contributes to the gravitational field. Webb has been studying some of the most powerful gravitational lenses known, and it's finding incredibly distant galaxies magnified by these cosmic telescopes. Some of these lensed galaxies are among the most distant objects ever observed, and they're giving us our earliest glimpses of galaxy formation. But Webb is also studying the lenses themselves, mapping out the distribution of dark matter in galaxy clusters with unprecedented precision. And here's what's interesting: the distribution of dark matter doesn't always match what our simulations predict. Some galaxy clusters have smooth, regular dark matter halos, while others have lumpy, irregular distributions. Some clusters show evidence of recent collisions, with dark matter clumps that haven't yet merged. Understanding these differences is helping us refine our models of how galaxy clusters form and evolve. One particular gravitational lens that Webb has studied in detail is called SMACS 0723. It's a massive galaxy cluster acting as a lens for dozens of background galaxies, and Webb's image of this region is stunning. You can see arcs and smears of light from galaxies that have been distorted by the cluster's gravity. You can see tiny, faint galaxies that existed when the universe was young, their light amplified and brought into view by the lensing effect. But more than just being pretty pictures, these observations are data-rich. Each lensed galaxy's position, shape, and brightness tells us something about both the galaxy itself and the lensing cluster. By analyzing all this information together, astronomers can reconstruct the three-dimensional distribution of dark matter in the cluster, trace the history of galaxy formation in the background galaxies, and test our theories of both gravity and cosmology. Now I want to talk about something that might seem like a detour but actually ties into everything I've been discussing: the nature of time itself. When we look at distant objects with Webb, we're not just looking across space. We're looking back in time. The light from a galaxy 13 billion light-years away left that galaxy 13 billion years ago, when the universe was a fraction of its current age. This means that everything we see in Webb's deep field images is history. We're not seeing what these galaxies look like today. We're seeing what they looked like billions of years ago. Those galaxies have continued evolving, forming new stars, perhaps merging with other galaxies, and if we could somehow instantaneously teleport to their current locations, we'd find them drastically changed from what we see in our images. But here's the deeper point: the concept of now across cosmic distances is actually ambiguous. Because of the finite speed of light and the effects of relativity, there's no absolute, universal definition of simultaneous events at different locations in space. What we call now on Earth is different from what an observer in a distant galaxy would call now. Time itself is interwoven with space in a four-dimensional fabric that Einstein called spacetime. And when we think about the early universe, this gets even more profound. The Big Bang wasn't an explosion that happened at a point in space. It was the beginning of space itself. Before the Big Bang, the concepts of space and time as we know them didn't exist. Asking what happened before the Big Bang is like asking what's north of the North Pole. It's a question that doesn't quite make sense because the framework needed to answer it doesn't apply. Webb's observations of the early universe are taking us as close as we've ever gotten to that boundary, that moment when space and time came into being. We're seeing light that has been traveling for over 13 billion years, light that started its journey when the universe was less than 3% of its current age. We're probing an era when the fundamental properties of the universe were still being established, when the first structures were just beginning to form out of the primordial smoothness left over from the Big Bang. And what Webb is showing us is that even at these early times, the universe was already complex, already structured, already teeming with activity. It's as if we expected to find a blank canvas and instead found a partially completed painting. The artist had already sketched the outlines, mixed the colors, and started filling in the details. And we're trying to understand how the artist worked so quickly, what techniques were used, what vision guided the brush. Let me share with you one more discovery that Webb has made, and this one is particularly mind-bending. Webb has been studying quasars, which are supermassive black holes actively consuming matter and shining with the energy of trillions of suns. Quasars are the brightest persistent objects in the universe, and they can be seen across vast distances. But Webb has found quasars at distances and epochs where, according to our theories, they shouldn't exist. Some of these quasars are shining when the universe is less than 700 million years old, and they're powered by black holes with billions of solar masses. As I mentioned earlier, there simply hasn't been enough time for these black holes to grow from stellar mass seeds through conventional accretion. But here's the additional twist. These early quasars don't look substantially different from quasars we see in the more recent universe. They have similar properties, similar spectral features, similar luminosities. It's as if the quasar phenomenon sprang into being fully formed, without a long period of evolution and development. And that's deeply puzzling. One possibility is that the first black holes, those seeds that grew into quasars, were indeed born massive through direct collapse or some other exotic mechanism. But another possibility, one that's even more radical, is that our understanding of black hole physics is incomplete. Maybe black holes in the early universe could accrete matter faster than we think is possible. Maybe the radiation pressure that should limit accretion doesn't work the same way under early universe conditions. Maybe gravity itself behaves differently on these scales and at these epochs. I want to emphasize that I'm not saying our theories of gravity are wrong. General relativity has been tested extensively and has passed every test with flying colors. But we also know that general relativity can't be the final word because it doesn't play nicely with quantum mechanics. There must be a deeper theory, a quantum theory of gravity, that unifies these two great pillars of modern physics. And maybe, just maybe, the effects of quantum gravity become important in the extreme conditions of the early universe or near supermassive black holes. Webb's observations might be giving us hints of these effects, subtle deviations from what we expect that point toward the deeper theory we haven't yet discovered. Or maybe not. Maybe the explanation is more mundane, a missing piece in our astrophysical models rather than in fundamental physics. But the point is, we don't know yet, and that's what makes this so exciting. We're at the edge of our understanding, and Webb is pushing us further, forcing us to question our assumptions and explore new ideas. Now, let me tie all of this together. What Webb has shown us over the past few years is that the universe in its youth was far more active, far more structured, and far more complex than we anticipated. Galaxies formed earlier, grew faster, and became more sophisticated than our models predicted. Black holes appeared sooner and grew larger than we thought possible. Stars formed at prodigious rates, enriching the cosmos with heavy elements on timescales that seem impossibly short. All of these discoveries are pieces of a puzzle, clues to a mystery that we're still trying to solve. The mystery is, how did the universe go from the smooth, simple state revealed in the cosmic microwave background to the rich, complex cosmos we see today? What processes drove this transformation? What physics governed the early universe? And what does all of this tell us about the fundamental nature of space, time, matter, and energy? We don't have complete answers yet. But we're making progress. Every new observation from Webb, every new data point, every new spectrum and image is helping us refine our theories and develop new ones. We're learning that the universe is more than just a collection of stars and galaxies. It's a dynamic, evolving system with feedback loops, phase transitions, and emergent properties that we're only beginning to understand. And here's what really gets me excited. Webb is just getting started. It's designed to operate for at least 10 years, possibly longer if everything goes well. Over the next decade, it's going to observe thousands more galaxies, hundreds more supernovae, dozens more exoplanets. It's going to map the cosmic web in unprecedented detail. It's going to study the atmospheres of Earth-like worlds. It's going to peer even deeper into space and further back in time. Each of these observations has the potential to surprise us, to challenge our theories, to reveal new aspects of the cosmos we hadn't anticipated. And while I can't predict exactly what Webb will find, I can say with confidence that it will continue to transform our understanding of the universe. Because that's what happens when you give humanity a new eye to observe the cosmos. We see things we never imagined, we ask questions we never thought to ask, and we discover that the universe is even more wonderful, even more mysterious, even more awe-inspiring than we dared to dream. You know what I think about sometimes? I think about the fact that we live in an era when we can do this. For most of human history, the stars were unreachable, their nature unknowable beyond what we could deduce from their light. We told stories about them, we navigated by them, we wondered about them, but we couldn't study them scientifically. Then came the telescope, and suddenly the universe opened up. We discovered that Earth wasn't the center of everything, that the Sun was a star among billions in a galaxy, that our galaxy was one among billions in the observable universe. Each discovery expanded our cosmic perspective, pushing back the boundaries of ignorance and revealing ever more wondrous truths. But even with powerful telescopes on the ground and in space, there were limits to what we could see. The most distant reaches of the universe, the earliest epochs of cosmic history, remained frustratingly out of reach. We could theorize, we could model, we could extrapolate, but we couldn't observe directly. Until now. With Webb, we've broken through that barrier. We're seeing the universe as it was when it was young, watching the first galaxies form, witnessing the dawn of the cosmic age. And in doing so, we're not just satisfying our curiosity. We're answering profound questions about our origins, about how we came to be, about our place in the grand cosmic story. Because here's the thing, we are part of this story. The atoms in our bodies were forged in the hearts of stars that lived and died billions of years ago. The elements that make up Earth, that make up life, that make up you and me, were created through nuclear fusion in stellar cores and dispersed into space through supernovae. We are, quite literally, star stuff, as Carl Sagan so eloquently put it. But it's more than just sharing a common atomic origin with the stars. The processes that Webb is studying, the formation of galaxies and stars and planets, these are the processes that eventually led to the existence of life. The early universe had to form galaxies so that stars could form within them. Stars had to live and die to create the heavy elements needed for rocky planets. Planets had to form in the habitable zones of their stars where conditions might allow for liquid water. And somewhere in the cosmos, on at least one of those planets, chemistry became biology, and life emerged. That happened here on Earth about 4 billion years ago, but the stage was set much earlier. The elements needed for life were being created when the universe was less than 1 billion years old. The seeds of our existence were planted in the early universe, in those first generations of stars that Webb is now studying. And so when Webb looks back to the dawn of cosmic time, it's not just looking at ancient history. It's looking at our history, at the deep origins of everything we know and are. It's connecting us to the universe in the most fundamental way possible, showing us that we're not separate from the cosmos but integral parts of it. This perspective, this cosmic consciousness, is perhaps the most valuable thing that astronomy gives us. It's easy to get caught up in the details, to focus on the specifics of galaxy formation or black hole growth. And those details are important, they're what drive the science forward. But we shouldn't lose sight of the bigger picture, the profound implications of what we're learning. We're discovering that we live in a universe that's far older, far larger, and far more complex than our ancestors could have imagined. We're finding that the laws of physics, worked out in laboratories on Earth, apply across billions of light years and billions of years of cosmic time. We're seeing that the universe is comprehensible, that human minds can grasp its workings and predict its behavior, even if imperfectly. And we're learning that we're part of something magnificent. The universe isn't just a cold, empty void with some matter scattered here and there. It's a dynamic, evolving system that has given rise to stars, planets, and ultimately to us. We are the universe become conscious, able to look back at itself and understand its own history. That's what Webb is really doing. Yes, it's collecting data on early galaxies and black holes and exoplanets. Yes, it's testing theories of cosmology and structure formation. But at a deeper level, it's helping us understand ourselves and our place in the cosmos. It's revealing the story of where we came from and hinting at where we might be going. As I look at Webb's images and think about its discoveries, I'm reminded of a quote from the physicist Richard Feynman. He said that poets speak of the beauty of a flower, but he, as a scientist, could see additional beauty in the flower that others might miss. He could appreciate not just the flower's aesthetic appearance but also its inner workings, the cells and molecules and processes that make it live and grow. And he could see the flower as part of a larger story, connected to the evolution of life on Earth, to the physics of photosynthesis, to the chemistry of DNA. The same is true for what Webb is showing us. Yes, the images are beautiful in their own right. The swirls of galaxies, the pillars of gas and dust, the arcs of gravitational lenses. They're visually stunning. But when you understand what you're looking at, when you know the science behind the images, they become even more beautiful. Every galaxy represents billions of years of cosmic evolution. Every star is a nuclear furnace transforming elements. Every planet might be a world where some form of life could arise. And the most amazing part is that we've only scratched the surface. The universe is vast, containing hundreds of billions of galaxies, each with hundreds of billions of stars. And Webb can only observe a tiny fraction of it. There are countless galaxies we'll never see, countless stars we'll never study, countless worlds we'll never visit. The universe's secrets far outnumber the answers we've found. But that's not discouraging. That's exciting. That means there's always more to discover, always new mysteries to solve, always new frontiers to explore. The universe will never stop surprising us, never stop challenging our understanding, never stop rewarding our curiosity. And in a way, that's fitting. Because curiosity is what makes us human. It's what drove our ancestors to venture beyond their villages, to cross oceans, to climb mountains. It's what inspired us to build telescopes and spacecraft, to split atoms and decode DNA. And it's what will drive us forward into the future, as we continue to explore the cosmos and our place within it. Webb is a testament to that curiosity, to our desire to know and understand. It's one of the most sophisticated machines humanity has ever built, the product of thousands of scientists and engineers working over decades. It represents billions of dollars of investment, countless hours of labor, and an unwavering commitment to pushing the boundaries of what's possible. And all of that effort, all of that investment, is dedicated to a single goal: to see further, to learn more, to understand better. Not for profit, not for power, but simply for the sake of knowledge itself. In a world often divided by conflict and driven by short-term thinking, projects like Webb remind us of what we can accomplish when we work together toward common goals. The data Webb collects belongs to humanity. Scientists from around the world, from different countries and cultures and backgrounds, collaborate to analyze it. Students in classrooms see the same images that researchers in universities study. The discoveries Webb makes become part of our collective human knowledge, enriching all of us. This is science at its best, driven by curiosity, guided by evidence, and shared openly. And it's a model for how we might approach other challenges facing humanity. The same spirit of international cooperation, evidence-based reasoning, and long-term thinking that built Webb and continues to operate it, that's what we need to tackle climate change, to cure diseases, to build a better future. But I'm getting philosophical here. Let me bring this back to the specifics of what Webb has found, because I want to leave you with a sense of the incredible discoveries we've discussed and what they mean. Webb has shown us that the early universe was far from the simple, primitive state we expected. It was already forming massive galaxies, growing supermassive black holes, and producing heavy elements at rates that challenge our theories. This tells us that the processes driving cosmic evolution are more efficient or work differently than we thought. It's found galaxies and black holes where they shouldn't exist according to our timeline, forcing us to reconsider how structure forms in the universe. Maybe dark matter plays a different role in the early universe. Maybe feedback from stars and black holes works differently. Maybe there are processes we haven't even considered yet. It's detected chemical signatures in the atmospheres of distant exoplanets, bringing us closer to answering whether life exists beyond Earth. The diversity of worlds we're finding is staggering, and it's expanding our conception of where life might arise. It's revealed details about star formation, supernova explosions, and galaxy collisions that are helping us understand how the Milky Way came to be and how our solar system formed. We're seeing our own past written in the light from distant objects. It's providing data that bears on the Hubble tension and other cosmological puzzles, potentially pointing us toward new physics or refining our understanding of existing theories. The answers we find might reshape our understanding of space, time, and gravity itself. And it's doing all of this while capturing images of breathtaking beauty, reminding us that the universe is not just a subject for scientific study but also a source of wonder and inspiration. So when you look up at the night sky, when you see those distant points of light, remember what they represent. They're not just stars. They're suns like ours, possibly with planets, possibly with life. They're parts of galaxies, vast islands of billions of stars separated by mostly empty space. They're participants in a cosmic dance that's been going on for over 13 billion years and will continue for trillions more. And remember that we, sitting here on this small planet orbiting an ordinary star in an average galaxy, we have the remarkable ability to understand all of this. Through observation and reason, through mathematics and experiment, we can decode the universe's secrets. We can trace our origins back to the Big Bang. We can predict the future evolution of the cosmos. We can ask why the universe is the way it is, and sometimes, amazingly, we can find answers. That's the legacy of Webb. That's what these discoveries represent. They're not just facts to be memorized or data to be analyzed. They're pieces of the greatest story ever told, the story of how the universe came to be and how we came to be part of it. And the story is still being written. Every day, Webb sends back new data. Every week, scientists publish new analyses. Every month, we learn something new about the cosmos. The revelations I've shared with you today are just the beginning. In the years to come, Webb will undoubtedly make discoveries we can't even imagine right now, discoveries that will once again force us to revise our understanding and expand our perspective. Because that's what science does. It challenges us. It surprises us. It shows us that the universe is far more interesting than our theories suggest. And while that can be frustrating when our pet theories are proven wrong, it's also deeply exciting. It means we're learning, we're growing, we're getting closer to the truth. The universe doesn't care about our theories. It simply is what it is, operating according to physical laws that we're slowly uncovering. And our job as scientists, as humans, as conscious beings trying to understand our place in existence, is to observe as carefully as we can, to think as clearly as we can, and to follow the evidence wherever it leads. Sometimes it leads us to uncomfortable places, to conclusions that challenge our assumptions or upset our neat models. Sometimes it leads us to profound insights that unify disparate phenomena and reveal deep connections we hadn't noticed. And sometimes it leads us to new mysteries, to questions we didn't know we should be asking. All of these outcomes are valuable. All of them advance our understanding. And all of them are part of the scientific process, the greatest tool humanity has ever developed for understanding reality. So as we continue to study Webb's observations, as we grapple with the puzzles it's revealed, as we work to build new theories that can explain what we're seeing, we should remember that we're engaged in something fundamentally human. We're exercising our curiosity, our creativity, our capacity for wonder. We're reaching beyond ourselves, beyond our planet, beyond our time, to connect with the vastness of space and the depths of cosmic history. And in doing so, we're not diminishing ourselves. We're not showing how small and insignificant we are. Quite the opposite. We're demonstrating the remarkable capacity of conscious minds to comprehend the cosmos. We're proving that intelligence, wherever it arises, has the power to understand the universe that gave it birth. That's something to be proud of, something to celebrate. Yes, we're small compared to galaxies and insignificant compared to cosmic timescales. But we're not nothing. We're conscious, thinking beings who can look at the light from a galaxy 13 billion light-years away and deduce its properties, its distance, its age, its composition. We can look at the faint glow of the cosmic microwave background and see in it the seeds of all cosmic structure. We can look at the spectrum of a distant exoplanet and identify the molecules in its atmosphere. These are not small achievements. These are triumphs of human intelligence and perseverance. They're the result of centuries of scientific progress, building on the work of countless individuals who dedicated their lives to understanding nature. From Galileo pointing his telescope at Jupiter's moons to Newton formulating the laws of motion and gravity, from Einstein revolutionizing our understanding of space and time to Hubble discovering the expansion of the universe, from the first X-ray satellites to the Hubble Space Telescope to now Webb, each step has built on the last, each generation standing on the shoulders of those who came before. And this process will continue. Webb is an incredible tool, but it's not the end of the story. Even now, astronomers are planning its successors, telescopes even larger and more sensitive. They're designing missions to search for life on other worlds, to map the universe in new ways, to test fundamental physics in extreme environments. The next generation of discoveries awaits, and who knows what they'll reveal. Maybe we'll find definitive evidence of life beyond Earth. Maybe we'll detect gravitational waves from the Big Bang itself. Maybe we'll discover new fundamental particles or forces. Maybe we'll figure out what dark matter and dark energy really are. Maybe we'll even find evidence of other universes, confirming theories of the multiverse that currently seem like pure speculation. Or maybe we'll discover something entirely unexpected, something we can't even conceive of right now. That's happened before in the history of science, and it'll happen again. The universe has a way of surprising us, of being stranger and more wonderful than our imaginations. And that's ultimately why we explore. Not because we know what we'll find, but because we don't. Not because the journey is easy, but because it's hard. Not because the answers are obvious, but because they're hidden, waiting to be discovered by those brave enough or curious enough or stubborn enough to seek them out. So when you hear about Webb's discoveries, when you see its images, when you read about the puzzles it's revealed and the questions it's raised, don't just file them away as interesting facts. See them for what they really are, pieces of a grand adventure, the adventure of conscious beings trying to understand the universe they inhabit. We don't know how this adventure will end. We don't know what the final answers are or even if there are final answers. But we know that the journey itself is worthwhile, that each discovery enriches our understanding and enhances our appreciation for the cosmos. And we know that we're privileged to live in a time when we can participate in this adventure, when we have the tools and knowledge to explore the universe in ways our ancestors couldn't have dreamed of. We're the generation that's seeing the early universe for the first time, that's finding planets around other stars, that's potentially on the verge of discovering life beyond Earth. What a time to be alive. What a universe to live in. And what a privilege it is to be able to look up at the night sky and know, really know, what's out there and what it all means. That's the gift that Webb is giving us. Not just data, not just images, but understanding, connection, wonder, a deeper appreciation for the cosmos and our place within it. And as we continue to receive data from this remarkable telescope, as we continue to puzzle over its discoveries and revise our theories to account for what we're seeing, we're writing the next chapter in humanity's story of cosmic exploration. We're adding to the body of knowledge that future generations will inherit and build upon. We're doing our part to advance human understanding, to push back the boundaries of ignorance, to shine light into the darkness. In a universe that's mostly empty space, mostly dark matter and dark energy we don't understand, on a small rocky planet orbiting an average star, conscious beings have arisen who can look out at the cosmos and comprehend it. That's extraordinary. That's profound. That's worth celebrating. So here's to Webb, to the scientists who designed and built it, to the astronomers who use it to explore the universe, and to all of us who benefit from the knowledge it's producing. Here's to human curiosity and ingenuity. Here's to asking big questions and seeking answers. Here's to the adventure of cosmic discovery. The universe has been waiting 13.8 billion years for us to look this deeply into its history. And now that we're finally here, now that we have the technology to peer back to the cosmic dawn, what we're finding is that the universe is even more amazing than we imagined. The discoveries keep unfolding, and each one seems to chip away at what we thought was solid bedrock. Take, for instance, what Webb has revealed about the cosmic dark ages. For decades, we assumed this period between recombination, when the universe became transparent, and reionization was essentially dormant. A quiet interlude where nothing much happened except hydrogen atoms floating in darkness, waiting for the first stars to ignite. Wrong. Webb is detecting faint signals suggesting the dark ages weren't dark at all. There might have been exotic energy sources we never accounted for. Perhaps the decay of massive dark matter particles was pumping energy into the universe. Perhaps primordial black holes, remnants from the earliest moments after the Big Bang, were already accreting matter and radiating. Perhaps there were even stranger phenomena, quantum effects operating on cosmological scales that our theories haven't predicted. The implications are staggering. If the dark ages were luminous, if energy was being injected into the universe during this supposedly quiet period, then our entire thermal history of the cosmos needs revision. The temperature evolution, the formation of the first molecules, the conditions that allowed the first stars to form, all of it would be different from what we've modeled. And speaking of the first stars, let me tell you about population 3 stars, because Webb is getting tantalizingly close to actually seeing them. These theoretical giants, composed purely of hydrogen and helium, should have been monsters. Without heavy elements to help cool collapsing gas clouds, the first stars would have been massive, perhaps 100 or even 300 times the mass of the Sun. They would have burned blue hot, lived fast, and died young, exploding as parent stability supernovae that completely obliterated them, leaving no remnant behind. We've never seen a population 3 star. They should be extinct, died out billions of years ago. But Webb might have found their signature. In some of the most distant galaxies, there are spectral features that match what we'd expect from stars with absolutely zero metal content. The evidence isn't conclusive yet, we need more observations, but if confirmed, it would be the first direct detection of the universe's first generation of stars. Imagine what that means. We'd be seeing the cosmic pioneers, the stars that first illuminated the universe, that first forged elements heavier than helium, that first enriched the cosmos with the building blocks of planets and life. These stars set everything in motion. Without them, we wouldn't exist. And what might actually let us witness them across the vast gulf of cosmic time. But here's something that's really making physicists scratch their heads. Webb has been measuring the metallicity, the abundance of heavy elements, in different regions of early galaxies. And the distribution doesn't make sense. You'd expect a gradient, with more metals near the galaxy center where star formation has been ongoing the longest, and fewer metals in the outer regions. But some galaxies show uniform metallicity throughout, as if the heavy elements were somehow distributed evenly almost immediately after being created. How does that work? Stars produce metals in their cores and don't release them until they die. Even then, supernova ejecta don't travel instantaneously. They expand at speeds of thousands of kilometers per second, fast by terrestrial standards, but it still takes millions of years for that material to spread across a galaxy. Yet Webb is seeing chemical homogeneity in galaxies that shouldn't have had time to mix their contents. Unless there were mechanisms we haven't considered. Powerful galactic winds driven by intense star formation could redistribute material quickly. Or perhaps early galaxies experienced turbulent mixing, with gas flows churning the contents like a cosmic washing machine. Or maybe, and this is speculation, maybe there were exotic processes unique to the early universe that could transport material across vast distances rapidly. Every answer raises new questions. That's the hallmark of good science, isn't it? You solve one puzzle only to find 3 more hidden behind it. Now let me tell you about something Webb discovered that almost nobody predicted: ultra-compact dwarf galaxies in the early universe. These are strange objects, galaxies that are incredibly dense, with stars packed together far more tightly than in normal galaxies. We've known about them in the present-day universe, but we thought they were the stripped cores of larger galaxies, remnants left after gravitational interactions tore away their outer regions. But Webb is finding them in the early universe, long before there's been enough time for such violent interactions to be common. So if they're not stripped remnants, what are they? Are they a distinct class of galaxy that forms under early universe conditions? Are they the building blocks that will later merge to form larger galaxies? Are they something entirely different that we haven't categorized yet? The existence of these objects challenges our classification scheme for galaxies. We have nice categories: spirals, ellipticals, irregulars. But the early universe seems to have had a much richer variety of galaxy types, many of which have no present-day analogs. It's like discovering that early Earth had entire phyla of organisms that went extinct without leaving descendants, creatures so alien to modern biology that we'd struggle to classify them. And then there's the rotation curves. Webb has measured how gas moves within some early galaxies, and the velocities are peculiar. The rotation curves, which tell us how mass is distributed, sometimes indicate less dark matter than we'd expect, sometimes more. There's no consistent pattern, at least not one we've identified yet. This matters because dark matter should be predictable. It should follow certain distributions based on how structures collapse under gravity. If early galaxies had wildly varying dark matter content, that tells us something important about how dark matter and normal matter interacted during galaxy formation. Maybe the relationship between them was different in the early universe. Maybe dark matter could couple to normal matter more strongly back then, or maybe the way it clumps was influenced by conditions that no longer exist. Here's another puzzle Webb has uncovered: anomalously bright galaxy clusters in the early universe. Galaxy clusters are the largest gravitationally bound structures in the cosmos, containing hundreds or thousands of galaxies. This should take billions of years to assemble, with smaller groups gradually merging into larger ones. But Webb is detecting massive clusters that appear to be already well established when the universe is less than 2 billion years old. These clusters contain hot gas that emits X-rays, which we can detect even at great distances. The amount of hot gas and its temperature tell us about the cluster's mass and age. And what Webb's observations show, when combined with X-ray data from other telescopes, is that some of these early clusters are just as massive and evolved as clusters in the present-day universe. That shouldn't be possible. Or rather, it should be extremely rare, requiring special circumstances. Maybe these clusters formed in regions of space where the initial density fluctuations from the Big Bang were unusually strong. Maybe they represent the peaks of the cosmic web, the places where multiple filaments intersect and matter collects most efficiently. But even then, the timeline seems compressed. Some cosmologists are proposing that we need to revise our understanding of how structure forms on the largest scales. Maybe the growth of cosmic structure isn't as smooth and hierarchical as we thought. Maybe there were periods of accelerated growth, triggered by phase transitions in the dark energy, or changes in the properties of dark matter. Maybe the universe's expansion history is more complex than our models assume. And this ties back into the Hubble tension in unexpected ways. If the universe's expansion rate has varied over time in ways we haven't accounted for, that would affect both the formation of structures and our measurements of cosmic distances. The puzzle pieces might all be connected, different symptoms of the same underlying issue with our cosmological model. Let me shift focus to something Webb has revealed about the intergalactic medium, the gas that exists between galaxies. This isn't empty space. It's a sparse but extensive reservoir of gas, mostly hydrogen, that pervades the universe. And Webb has been studying how this gas evolved over cosmic time. What's fascinating is that the intergalactic medium appears to have been heated and ionized earlier than we expected, and the heating pattern is patchy. There are regions that became hot and ionized first, and other regions that stayed cool and neutral longer. This patchwork pattern tells us about how radiation from the first galaxies propagated through space, how it carved out bubbles of ionized gas that gradually expanded and merged. But the details don't quite match our simulations. The bubbles seem larger than predicted, suggesting the first galaxies were more luminous or more numerous than we thought. Or perhaps the intergalactic medium was less dense in some regions, allowing ionization to spread faster. Or maybe there were additional sources of ionizing radiation that we haven't identified. Some researchers are suggesting that accreting black holes might have contributed more to reionization than we've credited them for. Black holes don't just swallow matter, they're incredibly inefficient eaters. Most of the matter spiraling toward a black hole gets heated to millions of degrees and radiates enormous amounts of energy before crossing the event horizon. This radiation includes copious amounts of ultraviolet light that can ionize hydrogen. If early black holes were more common than we thought, if they were actively feeding when the universe was young, they could have been major players in reionization. And Webb's detection of so many early quasars supports this idea. But quantifying their contribution requires understanding how much time these black holes spent actively accreting versus dormant, and that's something we're still working out. Here's something that keeps me up at night. Webb has found evidence of feedback mechanisms in early galaxies that are far more powerful than we observe today. Feedback is the process by which star formation and black hole activity regulate themselves. When stars form, their radiation and stellar winds push gas around. When massive stars explode as supernovae, they inject tremendous amounts of energy into their surroundings. And when black holes accrete, they can launch jets and winds that clear out gas from entire galaxies. All of this feedback should limit how quickly galaxies can form stars. It's a self-regulating process. Too much star formation produces too much feedback, which shuts down star formation, which reduces feedback, which allows star formation to resume. It's a cosmic thermostat. But in the early universe, this thermostat seems to have been set differently. Webb is observing galaxies with incredibly powerful outflows, gas being expelled at thousands of kilometers per second, carrying away significant fractions of the galaxy's mass. These outflows are energetic enough to potentially unbind gas from the galaxy entirely, preventing it from ever falling back and forming new stars. Yet these same galaxies are forming stars at prodigious rates. How can they maintain such intense star formation while simultaneously ejecting so much gas? Either they're replenishing their gas supply extremely efficiently, pulling in fresh material from the intergalactic medium faster than they're expelling it, or the relationship between star formation and feedback is more complex than we understand. Some models propose that early galaxies experience bursty star formation, with periods of intense activity followed by quiescent periods. During the active phases, star formation would be so rapid that feedback couldn't shut it down immediately. Only after hundreds of millions of years of accumulated supernova explosions would enough energy build up to blow out the gas and terminate the starburst. Then the galaxy would remain quiet until it could accumulate enough new gas to trigger another burst. If this bursting mode was the norm in the early universe, it would explain many of the peculiarities Webb is seeing. It would explain why some early galaxies appear so luminous and active while others seem dormant. It would explain the rapid chemical enrichment, since each burst would produce a new generation of stars that would enrich the gas before the next burst. And it would explain why early galaxies look so different from present-day galaxies, which generally form stars more steadily. But here's the catch: we don't fully understand what triggers these bursts. Is it galaxy mergers? Is it gas accretion from the cosmic web? Is it some internal instability that periodically triggers collapse? The answer probably varies from galaxy to galaxy, and teasing apart the different contributing factors is a major goal of current research. Now, let me tell you about something truly exotic that Webb might have glimpsed: primordial magnetic fields. We know that magnetic fields pervade the universe today. Galaxies have magnetic fields, galaxy clusters have magnetic fields, even the intergalactic medium has weak magnetic fields. But where did these fields come from originally? One possibility is that they were generated by stars and galaxies, with dynamo processes amplifying small seed fields into the large-scale fields we see today. But that requires seed fields to start with, and we're not sure where those seeds came from. Another possibility is that magnetic fields were present in the very early universe, perhaps generated during inflation or during phase transitions in the first fraction of a second after the Big Bang. Webb has observed polarized light from some very distant galaxies, and the polarization patterns might, just might, be telling us about magnetic fields in the early universe. Magnetic fields can align dust grains, and when light scatters off aligned dust, it becomes polarized in a specific pattern. By analyzing this polarization, we can infer properties of the magnetic field. The data is preliminary, and there are other explanations for the polarization patterns Webb is seeing. But if confirmed, if we really are detecting primordial magnetic fields, it would be evidence of processes occurring in the first moments after the Big Bang. It would connect Webb's observations to physics operating at energy scales we can't reproduce in any laboratory, physics that governed the universe when it was hotter and denser than the core of any star. Let me talk about something Webb has revealed regarding the morphology of early galaxies. When you look at galaxies in the present-day universe, you see clear structures. Spiral galaxies have beautiful winding arms and central bulges. Elliptical galaxies are smooth and featureless. Irregular galaxies are chaotic but still have identifiable bright regions where star formation is occurring. Early galaxies don't fit these categories neatly. Many of them are clumpy, with multiple bright knots of star formation scattered throughout. These clumps can be as massive as 1 billion suns worth of stars, formed in compact regions just a few hundred light-years across. They're like mini starbursts occurring simultaneously within a single galaxy. What happens to these clumps? Do they migrate toward the galaxy's center through dynamical friction, eventually merging to form the bulge of a spiral galaxy? Do they get disrupted by tidal forces and feedback, spreading their stars throughout the galaxy? Or do they remain intact, becoming globular clusters, the ancient stellar populations we still see orbiting the Milky Way today? Webb's observations are providing clues, but the picture isn't clear yet. Some clumps appear to be merging, while others seem stable. Some are being disrupted by feedback, while others persist. Understanding the fate of these clumps is crucial for understanding how galaxies evolved from the chaotic systems of the early universe into the more ordered structures we see today. And here's a related mystery. Webb has detected what appear to be isolated star-forming clumps in the early universe, not associated with any obvious galaxy. These orphan clumps are forming stars actively, but they don't seem to be part of a larger structure. Are they the seeds of future galaxies? Are they fragments ejected from galaxies during interactions? Are they something else entirely? If they're proto-galaxies, then galaxy formation might not always proceed through the collapse of a single large gas cloud. Instead, galaxies might assemble from multiple independent clumps that form separately and later merge. This would be a more chaotic, bottom-up process than we've typically envisioned. Alternatively, if these clumps are ejected material, they tell us about violent processes occurring in early galaxies. Maybe feedback is even more powerful than we thought, capable of not just expelling gas but also flinging out entire bound systems of stars. These escaped clumps would then wander the universe as orphans, perhaps eventually being recaptured by other galaxies, perhaps remaining isolated indefinitely. Now let's discuss something that bridges astrophysics and fundamental physics: gravitational wave sources in the early universe. We can't detect gravitational waves directly with Webb. It's an optical and infrared telescope, not a gravitational wave detector. But Webb can identify potential sources of gravitational waves by finding binary black holes, merging galaxies, and other systems that would produce these ripples in spacetime. And Webb has found some peculiar candidates. There are galaxies that show evidence of dual supermassive black holes orbiting each other, systems where two galaxies have merged and their central black holes haven't yet coalesced. These dual black holes are predicted to eventually merge, producing gravitational waves strong enough to be detected by future space-based gravitational wave observatories. But the frequency of these systems in the early universe seems higher than expected. If binary supermassive black holes were common when the universe was young, and if they were merging regularly, they would have produced a background hum of gravitational waves permeating the cosmos. This gravitational wave background might already be affecting the universe in subtle ways, influencing the motion of pulsars, the timing of signals from distant quasars, perhaps even leaving imprints in the cosmic microwave background. Detecting this background is one of the holy grails of gravitational wave astronomy, and Webb's observations are helping us predict where and when to look. By identifying black hole mergers across cosmic history, Webb is providing targets for gravitational wave observatories and helping us understand the cosmic merger rate. Let me tell you about Webb's observations of so-called dark galaxies, galaxies that contain very few stars but lots of gas. These objects were predicted theoretically but had never been convincingly observed before Webb. The idea is that some regions of space might have collected gas and dark matter but, for whatever reason, never triggered significant star formation. Maybe these dark galaxies are in environments where conditions aren't conducive to star formation. Maybe the gas is too hot or too turbulent. Maybe feedback from nearby galaxies is preventing the gas from cooling and collapsing. Whatever the reason, these galaxies represent a population we didn't know existed, and they might represent a significant fraction of all galaxies in the early universe. If dark galaxies are common, that has implications for our understanding of galaxy formation efficiency. We've typically assumed that most gas eventually forms stars, given enough time. But if there are large reservoirs of gas that never form stars, or form them only extremely slowly, then the universe is less efficient at converting matter into luminous objects than we thought. This could help explain some of Webb's puzzling observations. If there's a large hidden population of dark galaxies, they would contribute to the overall matter budget without producing light. They could affect the dynamics of galaxy clusters, providing additional gravitational mass. They could serve as reservoirs that occasionally feed gas to star-forming galaxies. And they would represent an entire aspect of the universe's ecology that we've overlooked. Here's something that connects to some of our earliest discussions. Webb has been studying the circumgalactic medium, the diffuse gas that surrounds galaxies and extends far beyond their visible edges. This gas is crucial because it's the interface between galaxies and the intergalactic medium. It's where gas from the cosmic web gets accreted onto galaxies, and where gas expelled by feedback from the galaxy first goes. Webb can study the circumgalactic medium using background quasars as backlights. When light from a distant quasar passes through the circumgalactic medium of an intervening galaxy, it produces absorption lines in the quasar's spectrum. By analyzing these absorption lines, we can determine the composition, temperature, density, and velocity of the circumgalactic gas. What Webb is finding is that the circumgalactic medium in the early universe was more extended, more metal-enriched, and more dynamic than around present-day galaxies. The gas shows signs of strong outflows and inflows, with velocities reaching thousands of kilometers per second. And the metal content suggests that feedback from the galaxy has enriched gas out to distances of hundreds of thousands of light years. This is telling us that early galaxies had a much larger sphere of influence than we realized. They weren't just isolated islands of stars. They were nodes in a vast network of gas flows, exchanging material with their surroundings, influencing and being influenced by the cosmic environment. Understanding this gas cycle is essential for understanding galaxy evolution. Galaxies don't evolve in isolation. They're constantly interacting with their surroundings, accreting fresh gas, expelling processed material, responding to influences from neighboring galaxies and the intergalactic medium. It's a complex, dynamic system, and Webb is giving us the first detailed look at how it operated in the early universe. Let me share one more discovery that's particularly intriguing. Webb has detected what might be prestellar cores in some of the most distant star-forming regions. Prestellar cores are dense clumps of gas and dust that are on the verge of collapsing to form stars, but haven't yet initiated fusion. They're the immediate precursors to stars, the seeds from which new suns will be born. Finding prestellar cores in the early universe is significant because it gives us a snapshot of star formation caught in the act. We're not just seeing the finished product, the young stars shining brightly. We're seeing the process itself, the moment before ignition. And what's remarkable is that these cores appear similar in many ways to prestellar cores we observe in nearby star-forming regions. This suggests that the fundamental physics of star formation, the collapse of gas under gravity, the fragmentation of clouds, the balance between gravity and pressure, this physics hasn't changed over cosmic time. Even though the early universe had different conditions, different metallicity, different radiation backgrounds, the basic process of how a cloud of gas turns into a star seems to be universal. But there are differences too. The masses of these early prestellar cores seem skewed toward higher values, suggesting that early generations of stars might have been systematically more massive than stars forming today. And the density and temperature of the cores are slightly different, reflecting the different environments they formed in. These observations are helping us calibrate our star formation models, giving us empirical data from a regime we've never been able to study before. And they're confirming some predictions while challenging others, exactly what we want from a new observatory. You know, as I think about everything Webb has revealed, I'm struck by a pattern. Almost every discovery has been surprising in some way. We expected to confirm our theories, and instead we've been forced to question them. We expected gradualism, and we're seeing rapid evolution. We expected simplicity, and we're finding complexity. This is how science advances. Not through the steady accumulation of expected results, but through anomalies, through observations that don't fit, through puzzles that force us to think harder and deeper. Webb isn't just filling in the details of a picture we already understood, it's revealing that the picture itself needs to be redrawn. And we're just getting started. Webb has a planned mission lifetime of at least 10 years, possibly 20 if everything goes well. In that time, it will make tens of thousands of additional observations, study thousands more galaxies, analyze hundreds more exoplanet atmospheres. Each observation has the potential to surprise us, to reveal something new, to push our understanding forward. The universe is under no obligation to make sense to us. It doesn't care about our theories or our expectations. It simply is what it is, operating according to laws we're slowly, imperfectly uncovering. And that's okay. That's more than okay. That's exactly what makes this adventure so thrilling. Because every mystery solved reveals new mysteries. Every answer prompts new questions. Every discovery opens new avenues of inquiry. The universe is an endless source of wonder, and our capacity to explore it, to understand it, to be amazed by it, that capacity seems unlimited. So when you look at Webb's images, when you read about its discoveries, don't just see data. See opportunity. See the chance to learn something new, to understand something deeper, to connect with the cosmos in a more profound way. We're living in what might be remembered as a golden age of astronomy. Future generations will look back at this era with envy, wishing they could have been here when humanity first peered into the cosmic dawn, when we first saw galaxies forming, when we first analyzed the atmospheres of distant worlds. And they'll build on what we've learned. They'll take our discoveries and push further, ask deeper questions, find better answers. That's how progress works. Each generation stands on the shoulders of the previous one, reaching a little higher, seeing a little farther. Webb is our contribution to that ongoing journey. It's our generation's gift to the future, a tool for exploring the cosmos and a symbol of what humans can accomplish when we dream big and work together. The universe has been here for 13.8 billion years, and it'll be here for trillions more. But we're here now, with the ability to observe it, to study it, to understand it. What an extraordinary privilege. What an incredible responsibility. What an amazing adventure. Let me tell you about something Webb has uncovered that's completely rewriting our understanding of cosmic chemistry. We've always assumed that the periodic table of elements was built up gradually, generation after generation of stars. Hydrogen and helium from the Big Bang, then the first stars created carbon, oxygen, nitrogen. Their death seeded the next generation, which created heavier elements. A slow, methodical process spanning billions of years. But Webb is detecting europium, gold, platinum, and other heavy elements in galaxies that shouldn't have had time to produce them. These elements aren't made in normal supernovae. They require neutron star mergers, incredibly rare events where two ultra-dense stellar remnants spiral together and collide. When that happens, the extreme conditions create rapid neutron capture, the R process, which forges the heaviest elements in the periodic table. The problem is simple. Neutron star mergers should be exceedingly rare in the early universe. You need two massive stars to form close together, both to explode as supernovae, both to leave neutron star remnants, and then billions of years for those remnants to spiral together due to gravitational wave emission. The math says this should take longer than the age of the early galaxies Webb is observing. Yet there's the europium signal, clear as day in the spectroscopic data. Either neutron stars were merging far more frequently in the early universe than our models predict, or there's another mechanism for producing our process elements that we haven't identified. Some theorists are proposing that collapsar supernovae, rotating stellar cores that collapse directly to black holes, might produce these elements. Others suggest magnetorotational supernovae with powerful magnetic fields could do it. The implications extend beyond just chemistry. The abundance of heavy elements tells us about stellar populations, about the initial mass function of stars, about how often different types of stellar deaths occurred. If we're wrong about our process element production, we might be wrong about the entire stellar life cycle in the early universe. And here's something even stranger. Webb has found variations in the ratio of different isotopes of the same element in early galaxies. Isotopes are atoms with the same number of protons but different numbers of neutrons. On Earth, the ratios between different isotopes are remarkably constant because our solar system formed from well-mixed material. But in early galaxies, these ratios fluctuate wildly from one region to another. This tells us that the gas in early galaxies wasn't well-mixed. Different regions had different chemical histories, different contributions from different types of stars. It's like finding that parts of a cake have completely different ingredients, suggesting the batter was never properly stirred. This patchwork chemistry reveals that early galaxies were more heterogeneous, more chaotic than we imagined. Now let me shift to something that touches on the very nature of space itself. Webb has been measuring the distances to early galaxies with extraordinary precision, and when you plot these distances against the galaxy's redshifts, you get what's called the Hubble diagram. This diagram should follow a smooth curve determined by the universe's expansion history. But there are deviations. Small ones, subtle ones, but statistically significant. Some galaxies appear slightly closer than they should be for their redshift, others slightly farther. Now, measurement errors could explain some of this scatter, but the pattern seems non-random. There are regions of sky where galaxies systematically deviate in one direction, and other regions where they deviate the other way. What could cause this? One possibility is that we're seeing the effects of large-scale structure in the universe. If we happen to be in a region that's slightly underdense compared to the cosmic average, and we're looking toward an overdense region, the different expansion rates could create these patterns. But the magnitude of the effect seems larger than standard cosmology predicts. Another possibility, more radical, is that the universe's expansion isn't perfectly uniform. Maybe there are variations in the dark energy density across space, or maybe the expansion rate depends on direction, not just distance. Such anisotropies would violate the cosmological principle, the assumption that the universe looks the same in all directions on large scales. If confirmed, it would shake cosmology to its foundations. We need more data before drawing conclusions, but it's precisely these kinds of anomalies that lead to breakthroughs. Unexpected patterns in data have historically been harbingers of new physics. Webb has also revealed something peculiar about galactic angular momentum. Every galaxy rotates, and that rotation is characterized by angular momentum, a measure of how fast the galaxy is spinning and how its mass is distributed. In the present-day universe, there's a relationship between a galaxy's mass and its angular momentum, and this relationship reflects how galaxies form through the collapse of rotating gas clouds. But early galaxies don't follow this relationship. Some have far more angular momentum than expected for their mass, spinning much faster than they should. Others have less, rotating more slowly. And there's no obvious correlation with other properties like star formation rate or morphology. This is deeply puzzling because angular momentum is conserved. Once a system has a certain amount of spin, it can't just gain or lose it without external influence. So these anomalous angular momentum must be telling us about interactions, about torques applied by gravitational fields, about gas accretion patterns, about processes we haven't properly modeled. Maybe early galaxies experienced more frequent flybys with neighbors, gravitational interactions that transferred angular momentum between systems. Maybe the cosmic web's filamentary structure imparted spin as gas flowed along filaments and accreted onto galaxies at specific angles. Maybe early dark matter halos had different spin distributions than present-day halos. Whatever the explanation, it's clear that galaxy formation in the early universe was influenced by factors we haven't fully appreciated. The devil is in these details, and Webb is giving us those details for the first time. Let me tell you about quasar absorption systems, because Webb has found something absolutely bizarre. When you observe a distant quasar, its light passes through numerous clouds of gas scattered along the line of sight. Each cloud imprints absorption lines in the quasar's spectrum, and by analyzing these lines, you can determine the cloud's distance, velocity, composition, and physical conditions. Webb has discovered absorption systems that show impossible combinations of properties. There are clouds with temperatures that should ionize certain elements, but those elements appear neutral. There are clouds with densities that should make certain molecules abundant, but those molecules are absent. There are clouds with metallicities that don't match any known stellar population. These anomalous absorbers are rare, maybe 1% of all systems, but their existence demands explanation. Are they remnants of some exotic event, like a gamma-ray burst sterilizing a region of space? Are they regions where the radiation field has unusual properties? Are they influenced by magnetic fields in ways we haven't considered? Or, and this is the really exciting possibility, are they direct evidence of physics beyond the standard model? Could these clouds be tracing regions where dark matter is interacting with normal matter? Could they be locations where cosmic strings, hypothetical defects in spacetime from the early universe, are passing through? Could they be signatures of extra dimensions affecting how radiation propagates? I'm not saying any of these exotic explanations is correct. The mundane explanation is probably right. We're missing something about the astrophysics of these systems. But the point is that when you make measurements precise enough, when you look carefully enough, you find things that don't fit. And those misfits are where new discoveries hide. Webb has also been studying the Lyman alpha emission from high redshift galaxies, and there's an unexpected pattern. Lyman alpha is a specific wavelength of light emitted when electrons in hydrogen atoms drop from the second energy level to the first. It's one of the brightest emission lines in the spectra of star-forming galaxies, and it's a crucial diagnostic for understanding their properties. But Lyman alpha photons have to escape from the galaxy to reach us, and that's not always easy. Neutral hydrogen absorbs Lyman alpha very efficiently, so if a galaxy is surrounded by neutral gas, the Lyman alpha emission gets trapped and scattered. During the reionization era, when the universe was transitioning from neutral to ionized, the fraction of galaxies showing Lyman alpha emission should increase steadily as more of the intergalactic medium becomes transparent. Webb's data doesn't show that smooth transition. Instead, there are sudden jumps and plateaus in the Lyman alpha fraction as you look back in time. It's as if reionization proceeded in discrete stages rather than gradually, with periods of rapid ionization followed by periods where progress stalled. This staged reionization could happen if the sources of ionizing radiation weren't uniformly distributed. Maybe reionization was driven by rare, powerful sources rather than many weak ones. Maybe there were feedback effects where ionization fronts stalled when they reached dense regions that were harder to ionize. Maybe the topology of reionization was more complex than our simple models suggest, with percolating bubbles that grew and merged in complicated patterns. Understanding reionization topology matters because it affects everything from the thermal history of the intergalactic medium to the formation of small galaxies. If reionization was patchy and staged, it would have heated some regions earlier than others, creating a patchwork of temperatures and densities that would influence where and when galaxies could form. Here's another Webb discovery that's making waves: detection of molecular outflows from early galaxies at unprecedented distances. We've known that galaxies expel gas, but we thought most of that gas was hot, ionized, and atomic. Webb is seeing cold molecular gas, the stuff that forms stars, being expelled at high velocities. This is counterintuitive. Hot gas is easy to blow out, it's already energetic and wants to expand. But cold molecular gas is dense and gravitationally bound. Expelling it requires tremendous energy, and the fact that early galaxies were doing this so efficiently suggests feedback mechanisms were even more powerful than we realized. The composition of these molecular outflows is revealing too. Webb detects carbon monoxide, water, and more complex molecules being expelled. This means the feedback isn't just clearing out primordial gas, it's expelling chemically enriched material that was potentially on the verge of forming stars. The galaxy is shooting itself in the foot, ejecting the very material it needs for future star formation. But maybe that's the point. Maybe this self-regulation is what prevents galaxies from forming stars too quickly and exhausting their gas supply. By expelling enriched gas, galaxies slow their growth, allowing dark matter halos to accumulate more mass before the next burst of star formation. The ejected gas might later fall back, possibly reaccreting onto the same galaxy or feeding neighboring galaxies. This recycling of gas between galaxies and their surroundings, this galactic fountain model, is something we've proposed for nearby galaxies. Webb is showing us it was operating in the early universe, suggesting it's a fundamental aspect of how galaxies evolve. Now let me tell you about Webb's observations of galaxy protoclusters, the progenitors of today's massive galaxy clusters. These are regions where dozens or even hundreds of galaxies are found in close proximity, bound together by their mutual gravity but not yet fully relaxed into a virialized cluster. Webb has found protoclusters at epochs earlier than we expected them to exist. Remember, structure formation is supposed to be hierarchical, with small structures forming first and gradually merging into larger ones. But these protoclusters seem to have assembled remarkably quickly, with many massive galaxies already in place and interacting. What's particularly interesting is the diversity of galaxies within these protoclusters. There are intensely star-forming galaxies. There are quiescent galaxies that have somehow already shut down their star formation. There are dusty galaxies. There are AGN. The full zoo of galaxy types exists in these early protoclusters, even though the universe is supposed to be too young for such diversity to have developed. This suggests that environment matters more than we thought. Even in the early universe, galaxies in dense regions evolved differently than isolated field galaxies. The interactions, the mergers, the tidal forces, the shared gas reservoirs, all of these environmental effects were already operating and producing diverse outcomes. Understanding protoclusters is crucial for understanding galaxy evolution because the most massive galaxies in today's universe, the giant ellipticals at the centers of galaxy clusters, formed in these environments. Webb is showing us their birth sites, revealing the conditions that produced them. And speaking of massive elliptical galaxies, Webb has detected quenched galaxies, galaxies with no ongoing star formation, at surprisingly early times. These galaxies are massive, containing hundreds of billions of stars, but they're not making new stars. Their gas has been exhausted or expelled, and they're passively evolving, gradually reddening as their stellar populations age. Finding quenched galaxies in the early universe is shocking because quenching mechanisms shouldn't be efficient yet. In the present-day universe, galaxies quench through several processes. They can exhaust their gas supply, they can be stripped of gas by interactions with the hot intracluster medium, or AGN feedback can heat their gas and prevent it from cooling and forming stars. But in the early universe, galaxy clusters don't exist yet, so ram pressure stripping can't explain quenching. AGN feedback might work, but many of these quenched galaxies don't show signs of active black holes. And simply exhausting the gas supply seems unlikely because the universe is full of gas, and galaxies should be able to accrete more from their surroundings. So how did these galaxies quench? Maybe they formed all their stars in an incredibly intense burst, converting all available gas into stars so quickly that there was nothing left. Maybe they experienced a major merger that disrupted their gas supply and prevented further accretion. Maybe they're in environments where the gas is too hot or too turbulent to form stars, even though it hasn't been expelled. Each explanation has problems, and the likely answer is that different galaxies quench through different mechanisms. But the existence of massive quenched galaxies in the early universe tells us that galaxy evolution isn't a simple one-way street from star forming to quiescent. The journey is more complex, with multiple pathways and diverse outcomes. Webb has also revealed interesting correlations between galaxy properties and their large-scale environment. Galaxies near massive dark matter overdensities, locations where the cosmic web's filaments intersect, have different properties than galaxies in underdense regions or voids. Specifically, galaxies in overdense regions tend to be more massive, more metal-rich, and have older stellar populations. They also have lower gas fractions, meaning less of their mass is in gas and more is in stars. This makes sense if these galaxies have been forming stars longer or more efficiently, converting their gas into stars and enriching their interstellar medium with metals. But the magnitude of these correlations is stronger than models predict. Environment seems to matter more in the early universe than it does today, suggesting that the large-scale structure was already influencing galaxy evolution when the universe was young. The cosmic web wasn't just a passive scaffolding, it was actively shaping how galaxies grew and evolved. Let me share something about Webb's detections of high-velocity clouds in the early universe. High-velocity clouds are clumps of gas moving through the intergalactic or circumgalactic medium at speeds that don't match the surrounding material. In the Milky Way, we've known about these clouds for decades. They're thought to be either gas being accreted onto the galaxy or gas that's been expelled and is falling back.